So now that we've talked about the design of the Memoizer for use with the Java Executor Completion Service, let's go ahead and go into more detail about how to actually implement this Memoizer. And as we talked about before, the goal of the Memoizer is to cache stuff so you don't have to perform the same long-running computation over and over again. You can just look the results up in a cache. So here's how the Memoizer is implemented. You can take a look at the source code at the bottom of in the link at the bottom of the slide if you want to see the actual implementation in context. So Memoizer is a generic class that implements function, and that allows us to be able to transparently make an instance of Memoizer work wherever a function is needed. It defines a field, which is a map, which could be a concurrent hash map or a hash map or a synchronized map or something, depending on what you're trying to do. We also store a field that's the function that's going to be passed in to do the computation. And here's the constructor. You pass in a function, you pass in a map, and both of those parameters are then stashed away in the corresponding fields. And the reason we do this is we want both function and map to be parameterizable, because we want to be able to demonstrate how you could plug and play different implementations with different characteristics without changing our Memoizer implementation. Here is the apply method. Remember, because this is a function, because Memoizer implements the functional interface, it has to implement the apply hook method, the one and only abstract method defined in the functional interface. And what apply does is it takes the key and it returns the value that's associated with the key in the cache. Well, how does it get that knowledge? It uses the maps computeIfAbsent method. Now, again, this is a map. Let's assume for sake of argument, it's parameterized with ConcurrentHashMap, which it would be if we were using this in the way we're going to do it with our first prime checker app implementation. Now, it turns out that computeIfAbsent is only available on the map interface in Java 8 and beyond. Versions earlier than Java 8 don't support these atomic check then act semantic methods. And so, or at least doesn't support this one. And so in that case, you'd have to do something else, which we'll show later when we talk about future tasks in more detail. What's cool about the computeIfAbsent method is even if multiple threads simultaneously call computeIfAbsent concurrently for the same non-existent key, only one of them will perform the function call, and all the other ones will just wait until the function call is completed. So what we do is we call computeIfAbsent, passing the key in. Remember, the key in this case is going to be some prime number candidate. We want to know, is it prime or not? And the first time that this is called, in other words, the first time when there's no value associated with that key in the map, then the function's going to be called back. Its apply method will be called back in order to compute whatever the function does. And if the function, of course, is to check if a prime number, or if a number is prime, then that's what the function is going to do. But we can parameterize that function. And this is a good example of the lazy initialization pattern, or the first time in style pattern that you see a lot in concurrent and non-concurrent code. What that means is the first thread that comes through will do the computation, and it won't actually block. It'll go ahead and do the computation and then update the hash map with the corresponding value and then return it. But if any other threads show up when the key has not yet been associated with a value, they will all block until the first thread finishes the computation. So by the time the other threads, the ones that come later, are going to continue, the value will have been computed. And so they'll just get the value back. And you can see that the purpose of apply is to return the value associated with that key, which may have been computed or may have already existed, depending on whether a thread was the first one in to do the computation. There's also another method called remove, and as the name implies, or suggests, remove simply removes the key and its corresponding value from the Memoizer. So that's just a way to clean things up. And the way it works under the hood, of course, is if you parameterize this with a concurrent hash map, then its remove method will atomically remove that key from the map. And you don't have to worry about race conditions and atomicity and visibility and ordering and all those good things. That's all handled for you by the concurrent hash map's very clever implementation. So that's the end of the overview of how to actually implement a Memoizer using a concurrent hash map. Of course, you could use other kinds of maps as well. But if you use the non-concurrent map, if you use just like a good old-fashioned hash map or tree map, then you couldn't call this safely in a multi-threaded program without some other locking mechanism provided. And we'll talk a bit about that a little bit later.